mainly about, well, the subject of the conference in a sense, what's the relation between Higgs field and this construction, and namely, well, but rather not Higgs field, but that one should kind of generalize the notion of Higgs field to something which is not holomorphic but rather smooth, and well, everything will be smooth here. So. So the first of all, I'll give what's the definition of the cotangent. I'll think about the cotangent bundle. To T and hat, and I'll give actually three approaches to this space, and I'll explain that there is a relation between the three, and all the three. Well, the third one will give us something which is close to Tn without hat, or to Higgs field. So first definition of the cotangent bundle, just the first construction of the cotangent bundle, for construction one. It's just what Alexander was explaining in the two words. So we have well, complex structure. So higher complex structure. So, well, we will construct it as T star to higher complex structure, quotiented by higher diffeomorphism. This is a what can be done, how it can be done. So you take the well, the cotangent bundle. Well, higher complex structure is just a collection of mu2, etc. mu_n. These are all belong to k squared. Sorry, k 1 minus 2 comma 1 k squared minus 1 k 2 minus 1 minus 3 comma 1, etc. Or minus 1, etc.
It's just k bar.
K bar, sorry. Thank you. Just k bar. It should be something that T2, etc., Tn belongs to something which is complementary to this two, so it's K2, K3, etc. So we have a collection. Once again, this is written in one reference complex structure, which is actually nothing, does nothing, so we can change complex structure and recompute all these quantities. Well, this is just, these are mu's which are defining our higher complex structure, and these are cotangent vectors. So, cotangent vector and we want, of course, how to compute the cotangent bundle. We need to, well, the pairing between the two, so we have the symplectic form, or one form alpha, which will be equal to the integral of the surface delta mu I. That is Ti. We can integrate because of example I. We can integrate because it's here complementary dimensions. And therefore, the cotangent bundle is, one can write down explicitly the condition that we want that the cotangent bundle, that's the integral of, well, if we take any complex structure and deform it by a higher Hamiltonian, so if H is higher Hamiltonian, and then, well, then we want that the integral of sum of the integral of I delta mu I, where we just, this is a deformation of the mu I under the action of the higher Hamiltonian, Ti b equals to 0, for any h. So that this T must be orthogonal to any deformation by higher Hamiltonians, and this gives us certain condition on the operator T, which will be the conditions. Well, so T star of our space T hat will be equal to the correction at the point mu. It will be correction of T2, etc. Tm, such that there is some well, not very complicated by some operators, d bar plus something acting on Ti equals 0. So there is some operator which is deformation of operator d bar, which just integrate. And we can compute the dimension just by studying this operator and figuring out that the space of dimension of this operator is equal exactly to g minus 1 times n squared minus 1, which is the dimension which we expect.
So a higher Hamiltonian is a function which generates one of these higher diffeomorphisms?
Yeah, higher Hamiltonian is function generated by this diffeomorphism. So, well, one can write it down more explicitly. So if you have this form of p to the n minus mu p minus mu 2p minus mu 3p squared minus etc. So you can take Poisson bracket between them and the h.
It's p bar minus.
Pardon?
It's p bar minus mu 2p minus, no? It's the second term of the
yeah. P bar. Yeah. Of course. This, P bar minus something, and you can compute the compute bracket of that with h, which depends on p and p bar, which is just a function. You compute the Poisson bracket between the two, and you computed modulo your ideal, and well, the modulo ideal it's equivalent. Well, it's this Poisson bracket is equivalent modulo ideal to some delta mu 2p minus etc. minus delta h. Then minus 1 modulo the ideal.
So I'm missing that. What is the role of delta? And what is the delta?
Pardon?
Can you remind me what the delta is?
This is the definition delta mu. This is the definition. So you compute this Poisson bracket.
What type of? Okay.
You compute the Poisson bracket. You compute the modulo ideal.
Yeah.
Modulo ideal, every element represented is a polynomial. Well, zero's coefficient is 0 is just constant. You need to prove it, but it's 0. Yet, well, you get something, and this something is just the formation of your mu's under the action of this Hamiltonian.
So
by definition.
When you define alpha, you could have put mu there and it would have made sense, but you want to put delta there. I see. Okay.
Well, actually, I use delta in different sense, more or less, but here, just delta is one form. So alpha is one form within two-dimensional space. This alpha is one form within two-dimensional space. And this is something which you obtain if you insert the Hamiltonian vector field. Is this one form?
Yeah.
So this delta h is just a result of, well, maybe it's instead of delta h, it's the same thing as that mu is equal to L h mu. So strictly derivative with respect to mu. So just, well, this formula illustrates at least that the computation is quite straightforward. Even Hamiltonian, you can easily compute how the mu's change. So this is one way to obtain. So I obtain this equation, which I will denote by star. So this condition on the lattice T. Now another thing that now I will consider, forget for a moment, that I am in field 0. So suppose I will consider just the sections of Poisson bracket, symplectic structure on sections of help of T star of C. C star of C, complexified here. So, what is the nature of symplectic structure on this space? No, it's not anymore. Pardon? There are three, of course, but there is one. Well, there are two of them which are complex. Well, you mentioned there is another one. Another one somehow. Well, I doubt that there is a problem with that because we need really a metric on the surface, so this is a kind of complicated. But there is one. How to define it? Well, it's very easy. The only problem is that, well, they're very easy to define, and the definition is just, well, here, well, let's define first the symplectic structure on help of C2. What's the natural symplectic structure here? So it can be defined in the following way. So help C2 is just it's blow up of C. Well, it comes from symplectic structure on C squared to the n, which is terms comes from symplectic structure on C squared, which is just dx dy. It's a standard symplectic manifold. You can compute symplectic structure, then you use symplectic structure on the nth power, and then you go up and just figure you need to realize that this symplectic structure is actually non-degenerate. So the only thing I want to say is that this is write the formula for the symplectic structure. This symplectic structure is the following way. So you have on this space you have coordinates mu1, etc. mun, t1, etc. tn, and then the Poisson structure is right that mu I, mu j equals ti, tj equals 0, and mu I, tj equals ti minus j. With an additional, if I and j equals, if I is greater than j, it's equal 1 if I equals to j and 0 otherwise. Just simple exercise on computing Poisson brackets in this coordinates. So you see that mu's and t's are not really conjugated variables, but they almost conjugated. Well, to be honest, the conjugated variables to mu's are actually roots of the corresponding equation. So you have a polynomial of degree n with t's as the coefficients, you can find the roots, and these roots are really conjugated to mu's. But you see that this Poisson bracket is almost these mu's and t's are almost conjugated. Then t's are small, because these t's are small. This is almost 0, and you have nice Poisson brackets, and therefore you can extend this Poisson bracket to the sections of this infinite dimensional space and get exactly the same statement. That so if you have two sections Then you have the on infinite dimensional space, on the space of sections. Yeah, well, of sections on the space of the sections. Yeah. The Poisson bracket is given by the standard formula that dealt with you. Well, by the same formula actually, given by the same formula. Okay, so this is a remark about Poisson structure on the space of section of the Hilbert scheme.
So it will be the same formula at one point, but at different points it will be just commute.
Well, no, I want to write down, well, this, the same formula means that the Poisson tensor will be d over d mu I integral of, well, d over t I t I minus j. And when j is over I greater than j, something like that. Hopefully this works.
Sorry, I don't understand space of sections. Is there a map from your Hilbert scheme to something else of which you're taking sections? Or
Well, there is a, okay. There is a, we are speaking about the following object. We have been speaking the sections above a Riemann surface, or two-dimensional surface, with the following bundle on it. So you take the bundle of cotangent bundle, take the Hilbert scheme of it, and well, sections of this bundle over a surface.
so you take this Hilbert's
Point-wise,
Yes, point
Hilbert
Hilbert.
schemes.
Point-wise Hilbert schemes.
fiber-wise.
A bundle of
A bundle of Hilbert schemes, yeah.
So-
It's just
So it's
the previous talk, so
a
I'll
bundle
let
of
that sit
symmetric
here.
products. It's a bundle of symmetric products from the fibers.
It's Hilbert schemes.
Yeah, but the Hilbert scheme of the fiber is a curve.
No, it's Hilbert scheme. You consider two-dimensional fiber because it's complexified cotangent bundle. C2 is with every fiber.
I see.
And so you have something.
It's a bundle of Hilbert schemes over the.
Yeah, so I just repeat once again that if you have, instead of taking Hilbert sections, well, we have some space of higher complex structures. Complex structure, which was defined in last lecture, is the same thing as a section of the help 0 of T star C of C. Where 0 means that it's a Hilbert scheme above 0. Now I want to describe a cotangent bundle, and I want to explain that more or less this is this space which is well, just consider Hilbert 0, you consider Hilbert everything, and you get what you want.
So it's probably question please.
Yeah.
So this set, this is just a set inside this the function for the scheme.
It's a
Because of the non-degenerate conditions, right?
it's a plus non-degenerate condition.
So this is it's a stratified space which is stratified by action.
Yeah.
So this you're picking one of the problem.
I want to say the following, that this non-degenerate condition pulls out plenty of things. And so this pulls out everything which cannot be described in this way, plus something which you can. So it pulls out everything where the condition is mu2 bar equals 1, is, well, equals 1. This is excluded, plus everything which is not discrete.
But in closure,
It's a closure where plenty of other things. Yeah. In particular, not only something with m equals 1, mu 2 equals 1, but something also which is just some ideals with 1. Yeah.
all
All
young diagrams.
young diagrams,
This is
yeah.
very
You have in one point you have something like, well, one diagram in one point, another diagram in another point. You could have some, well, I honestly didn't study the generation, it's the next point of the picture, but the generation is more complicated than the complex situation. This is certainly the work. So we just, well, now we study the cotangent model. So you have this Poisson picture. One little remark that, well, Hilbert Hill 0 is not a Lagrangian submanifold with Hill, a Lagrangian subspace. But it's almost is. Because, well, it has dimension n minus 2, n minus 1. And Hilbert has dimension 2m, so it's a little bit less than what should be. So the way to go around, instead of considering the Hilbert space, what can consider is you take the Hilbert scale m of T star C of sigma, and you take the Hamiltonian quotient by C, which acts by translation. So it's just translations. And therefore, on this space, you have coordinates which are actually, well, what's the means Hamiltonian reduction with translation? Of course, the quotient will be symplectic manifold. And the quotient is, well, by this translation, you can, well, here are the coordinates.
I mean, this is a simplex manifold of which the functional scheme is the
It's Lagrangian. Here, yeah. Here, it's Lagrangian. The 0, 1 is Lagrangian here. And also the coordinates here are mu1, mu2, mu-n, and t2, tn. So we exclude, when we take a quotient, quotienting, it's the same, well, t1 is a Hamiltonian of this motion, so we take t1 equals 0, and then the quotient with respect to mu2, shifting of mu2. So this is just gives you. Yeah, you consider everything with respect to translation in one direction, and another one is excluded because it's a reduction of the point. So you may imagine that all these numbers are equal to actually to well, in particular T1 is 0, and everything is fine with that. Now I claim the following thing. So I can well, and then I may impose the following condition. So the sections, all the sections, well, among all these sections, one can ask what are the sections which are Lagrangian. Now Lagrangian in respect to just as the structure of the cotangent model. So claim that well, one can maybe I will write this down. We'll see with mu1 the section surface of the thing. That mu2 mu-m t of z, of course. T2, Tn gives the Lagrangian section. Of this hill of this hill of the star. Hill of the star. If, well, this is more or less obvious what it means. It means that I just write in formula that you want that the Poisson bracket between p bar minus T2P to the M minus 2 minus etc. comma
P to the n.
P to the N P bar minus mu 2 P minus etc. B0 modulo the ideal. And well, this is just a claim that, well, just equivalent to say that the corresponding section is Lagrange. But now well, and it gives me some relation between mu and t. This condition is just, you can write an equation, and these are some huge equations which relate mu and t. But what is the observation? That, so you have some condition that T2, Ti, well, this implies in some conditions on Ti's. And if you take this condition, well, you can compare this condition with the condition star, which I started with these equations. And that the claim, and this condition, in the limit where t squared equals to 0 coincide with star. So it means that if you write this condition, but then impose that you quotient by the ideal that t squared is 0, any products is just everything, keep linear part on t. So you get exactly the condition of Ti. So therefore, well, the moral of the story that what's the cotangent bundle to our Hilbert scheme? This is a kind of section of just not pointed Hilbert scheme, but just Hilbert scheme, but just in the vicinity, infinitesimal vicinity of the origin. So you should imagine the cotangent vector T star of M of my T hat, our space, as a space of well, what's the section of Hilbert's of this bundle? This is a spectral curve. By definition, spectral curve is a section of this bundle. It's something, it's cotangent bundle. So there is a cotangent bundle which has n-fold covering n times the base. So this is just a kind of spectral curves in the vicinity of 0 section. So this is one point of view on this, well, theorem or proposition. So you have this curve in the vicinity of 0 section. So you can imagine what is the period of this curve. So what's the curve in the vicinity of 0 section? You can imagine that as just a curve which is given by the equation with this equation. So, well, this equation, maybe, well, given by these two equations. You have a curve. This curve hence is Lagrangian in the limit. So we can compute the periods are 0, because if the curve is just smacked on the 0 section, they are 0. But we can compute the ratio of two periods, and they are not 0. So therefore, you have but on the other hand, we know that the ratio of all the periods of the Lagrangian submanifold is something which is invariant of the Hamiltonian action. So therefore, the coordinates on the space there is also, well, there's the same thing as periods of the Lagrange, the corresponding, the spectral curve. Well, strictly speaking, I cannot prove that in full generality. I know that there is a map between which is awkwardly from in this direction. So for any point here, you can construct a spectral curve. How to do that? You write these two equations, and then you tend all the coefficients to t to 0, and compute the periods, what we obtain, and then the periods is not defined as ratios are defined. So the answer you can define, you can obtain any periods you want. What is contrary to, you know, that the spectral curves for, if you consider Hitchin curves, then the periods are more or less half-dimensional. Well, the space of periods you can obtain is only half-dimensional, the space of all possible periods. If Lagrange space is homological curve. Here we have the whole space is homological. So otherwise, you have a curve with the homological class, and this is homological class. Well, this is the first statement. And another finally, what is the relation to Higgs bundles. So what is the? I want to say that what's the Higgs usual of Higgs bundle is just a connection. You have a connection number, well, flat connection. Maybe I will write down this like that. A of lambda is a flat connection having a form phi plus d plus lambda phi plus lambda inverse then phi bar. So if such a connection, then phi is usually endomorphism of vector bundle, but now I also have just omega 1 in endomorphism of this time of the cotangent bundle, well, of some vector bundle which is isomorphic, not canonically to cotangent bundle, right? I'm not pretending that this is the same thing.
So are you thinking of D as being unitary, taking an adjoint, or just
Pardon me? These two, psi is not unitary.
the D, the connection?
D is not, well, nothing is
Doesn't
unitary.
have
So
to
far,
be.
nothing is unitary.
Okay.
I want to yes. Here is the same thing. Omega phi bar, sorry, it belongs to omega 1 of various space, and phi bar as well. And we want also the following thing, that plus the condition that phi and phi bar are unimportant. So otherwise, from this condition, the flatness condition follows that phi squared equals phi bar squared equals 0. Yeah, because you compute the square of that, and this standard Hitchin condition. For Hitchin system, it's not important condition because phi is always square root 0 because this is just proportional to dz. But now we have just smooth form, and we want to impose this condition. And if we impose this condition, then it means that phi is equal to phi 1 dz plus phi 2 dz bar with respect to dz bar any coordinates. I could write this dy, and I want that these two matrices be important, and this condition implies that, well, phi 1, phi 2 are commuting in important matrices. they be non-degenerate in the sense that they have phi 1 and phi 2 have one cyclic vector. So in fact, this 2 phi 1 and phi 2 define, so they define a higher complex structure. Well, not higher complex structure, the section of Hilbert. But so far, without non-degeneracy condition, but define a section of L0.
So D you want to use flat. Like start with some flat.
I want that this be flat. So this is,
D is
let's
not
call A of lambda, and I want A of lambda squared be 0. So this is equivalent to the condition that phi squared is 0, phi bar squared is 0, d phi is 0, and d squared plus phi bar is 0, which is just anodes of Hitchin equation. The only difference that now there is no partition between bar and non-bar. All of them are just smooth. So now what I want to do is, so suppose we, well, now I formulate a theorem which I would like very much to prove, but I cannot. Yeah, but, so the conjectural theorem that for any higher complex structure well, I will denote it by just mu. There exists, well, and for, yeah, there exists phi bar and d, and v such that phi represents, in this sense, mu, it's bad to write it. Phi bar represents mu bar, and the corresponding connection is, well, the corresponding connection is flat. Phi plus phi bar plus d squared equals 0. And this, well, all these, in fact, and this is unique, and phi bar d are unique. I said something wrong for the moment. Okay, phi bar are unique up to Gaussian formation. So it's kind of analogue of the theorem of Hitchin, well, Corlett-Simpson Hitchin, but in a non-homomorphic setting. So, well, this theorem is not proven, but nevertheless I can suppose it is proven. So I want to say, I want to construct the following map. So I want for any solution of this equation, it will be 2 star modular gauge transformation, which is mapped to T star to T star of T at the end. So for any solution of this equation, one can associate a cotangent vector to my space, which is an analog of Hitchin's construction. So in this case, you have solution of Hitchin equation, which can be defined with flat connections, and it's an isomorphic cotangent bundle to the moduli of stable bundles. Here, instead of moduli stable bundles, you have cotangent bundle to this high Teichmüller space, and here is a solution of this equation, which is, once again, it's on one hand, I just forget about complex structure, on the other hand, I impose some condition, which is the condition of nilpotency, and the space dimension of the space of solution expected to remain unchanged, because every space has the space of solution, just the space of well, dimension n minus n square minus 1 times g minus 1. So how to do that? Well, the recipe is very simple. So suppose we have such a connection. So suppose we have a connection. So let's denote by nabla. Well, the connection H. Well, first of all, we pass to be lambda is something which is usually between 0 and 1, and H is something which is around 0. So we denote H bar H to be lambda inverse, and consider the well, the something nabla plus nabla bar B H times B lambda times inverse times my phi plus phi bar plus D. So I just multiply V by lambda inverse, so I get the lambda connection, lambda bar. This is something like H times D plus A of lambda, A of H. Here is something like H times D bar plus A bar of H. So it's one component of the connection, this is another component of the connection. And of course, I want these two to commute. Well, it's not the connection in the sense that, well, it's connection multiplied by a constant, so it's not.
So you're multiplying both nabla and the nabla bar by H.
I'm going to provide both of them. Yeah, I provide both of them to have something which starts with H and then with some higher power of H. So A of H is A0 of H, A0 plus A1H plus etc. So the first non-zero term will be with H0. And this is it. So you have for H equals 0, it's not a connection, it's not just an operator. For H higher, it's a connection. Now I want to construct out of this data, I want to construct my cotangent space. So first of all, from the construction, we see that A0 is just equal to phi. Well, or conjugated to phi. So, well, maybe it's better to write this space. Oh, it's not flying, it's just homomorphic particle. But, well, sorry. Yeah. Well, maybe I should try. So, easy proposition. So there exists a section of our bundle of, well, that in this case I'm speaking about of our bundle isomorphic of T star, bundle isomorphic to T star C of sigma, such that well, section V, such that nabla V, well, now V, now V, etc., now n minus 1V, form a basis. Locally, what means locally? Form a basis of sections.
So the proposition is there exists. You
The
wrote
proposition there exists.
Yeah,
There
you
exists,
wrote-
sorry. There exists. Thank you. There exists a section in the vicinity for h sufficiently small. Well, globally it exists. Well, there's some technical detail about its global existence. I would not want to speak about that. So the proposition there exists. So suppose we have this V, then we can write down the condition that now to the n V is equal to plus T1, T2, now n minus 2. Well, T1 n minus 2V plus Tn V equals 0. And of course we can express number bar of phi also is equal to plus T1 plus mu1. Number V plus mu2 mu plus mu2 number V plus mu3 plus mu1, sorry, number V squared V plus etc. equals 0. So we can extract my T and mu out of it is plus mu1. mu1, of course, here you should not mu1. So you can extract out of this V, you can extract the mu and T's. So, in fact, if you impose the condition, if you write down this condition that you can restore the connection, in adding the condition that the commutator of V and of number bar and number to the k equals 0 for any k less or equal to n minus 1, n minus 2. So, knowing that these two connections, well, it defines you actually a connection, these two relations. So if you have a collection of t's and a collection of mu's, then you can just construct a connection satisfying this condition. And then this connection is flat if now bar now to the n minus 1 equals 0. Well, if you have collection T1 and U, then this is 0 if and only if the claim, the connection number plus number bar squared equals 0 modulo h cubed if and only if the condition star is satisfied. So actually, if you compute this, you have connection defined by this condition. You compute this curvature in the sense of the only non-trivial element you have. You want it to be 0 modulo h cubed, and this implies this condition relating the cotangent bundle with, and therefore you have, so finally what it tells that for any solutions of my equation, I can construct, so conclusion, that the solution, well, this condition phi plus b plus phi bar equals 0. Well, sorry, it's written somewhere that therefore I constructed the map from solution to this thing. So the idea is just to take some vector and write down C and U from this space and obtain exactly this condition. So therefore, well, the main conjecture which we have is that vanishing of this curvature up to order 3 implies that actually, well, what was surprising for me is really of order 3, because usually if you have quantization, you do it up to order 2. But here, order 2 and order 3 gives you the desired conditions. Well, order 1, order 2 gives some trivial, order 1 gives some trivial things, order 2 that gives one trivial. So this is a, so the conjecture is that actually having, if we are sure that it vanishes, so we have a cotangent vector, so it means that it vanishes up to order 3, then you can canonically restore all the connection up to higher order, so it's kind of deformation quantization, then will give you the solution for the equation uniquely starting from the cotangent vector. Yes, and perhaps, well, it would be, of course, there is no chances to have it for sufficiently large value of t. There is this, for maybe should remark without writing, for this program for SL2, even for SL2 is not yet finished. So for SL2, this equation is equivalent to this famous Teichmüller equation, which is e to the phi, well, dd bar phi plus e to the phi equals e to the phi plus tt bar e to the minus phi, where this equation has a solution, so it has solutions only for integral of tt bar sufficiently, well, less than 2 pi I, 2 pi. 2 pi times the electron minus 2 pi times the electron of the surface. So there is some natural restriction that above that solution cannot exist. And they definitely exist in the vicinity of zero section of t. So really the solutions, it's not like fiction system where you have really a map with the image which is the whole thing. It's quite probable, and almost sure, that the image of this map is only part of, well, the vicinity of zero section. But in general, this is a, well, this is what we expect. Well, okay, I'll stop here. Thank you very much for.
So have you done?
Yeah.
So you want, we try to discuss the maps to fields and points in situ.
Yeah.
Present as a, so that's a capital portion of the vector space and it's spread by that capital portion of the vector space, which is then the equations which are provided in different equations, particularly will involve the cyclic vector, which is somehow doesn't feature.
Well, the cyclic vector appears here.
Is it? Oh,
It's actually, roughly, the V should be cyclic vector for every factor. So it's actually.
but then you see, look at the real mode that, which is something like the commutator phi with phi bar. And then the fish.
You mean, yeah.
That involves cyclic vector in the, it's not equal to 0, so you do this equal to
In my indication, the phi and phi bar. Well, it's not zero. Definitely here it's not zero.
Here it's just curvature. Just curvature of D, right?
It's a curvature of D here.
That's not enough. Is that what that would mean? So that means that you're imposing the equation. So this is like a vortex equation which describes quasi-maps into the
Not enough in which sense? Not enough
full
what?
instance,
Yeah.
the full instance. So that describes the quasi-maps into the syntactic portion where you impose the one map is commutative 5 phi bar is equal to 0. Whereas what you want is the commutative 5 with phi bar is equal to v dagger plus constant. Minus v dagger plus constant.
VB
Dagger,
dagger plus
constant.
constant. Yeah, this constant can be, well, if this is not zero, then this is zero, yeah?
That's the positive. V minus v.
Pardon?
Well, that's
You mean the third? You know, what is the main problem for me, at least for this story, so if you have really want to consider the third complex structure on the Hilbert scheme, it involves a magic on space. So heterogeneous structure in on C2 is actually on Euclidean four-dimensional vector space, the real vector space. And this is a magic. But here we have no such structure. Because magic on complexified tangent bundle implies in particular magic on the surface itself. So this is a structure which is not invariant under different physics. And for that reason, I just think that perhaps, well, it's not so simple. Of course, everybody wants to.
yeah, but that's then what guarantees that V is a cyclic vector? Otherwise, I don't know how to impose it.
No, cyclic vector with respect to phi. For a moment, we forget about phi bar.
This is the equation which guarantees that. So if you impose this equation, that would imply that
You mean
V is
this
cyclic with
equation?
respect to phi. So this equation, modular unit to this equation, is equivalent to
First of all, there is no unitary structure. Well, this is one thing which is, well, it's not unitary, it's rather real structure. So you have some action of this split form.
well, you
Yeah.
have
Well, I would like very much to have something like that. But so far, I don't know how to do that.
So maybe I missed the most important. Now, if you just think about if phi and phi bar in the quantum complex,
Yeah.
really the quantum complex then this looks like it's just a connection for the loop group.
Yeah, yeah. So that's for the loop group.
Why is it only why the expansion only bound by the first minus first powers?
No, it's just like in Hitchin situation that, well, there is a kind of very, if you really consider the loop group, then for some reason, if you really restrict your connection this way, then you get something like that. Of course, if you consider all connections in the loop groups, it's all possible, and you have some fusion international space, which is nothing but just loops in the space of orderly Fred connection, which is not interesting.
Well, in his case, since phi was 1, 0, type, so phi bar
Yeah.
was 0, 1 type, so there you could say that lambda is just the gradient of the Teichmüller, which comes from the construction of the surface.
You know, well, in a sense, it's almost the same thing, because acting by higher differomorphism, which amounts, of course, action of higher differomorphism is the same thing as the action of the gauge group, then you can get rid of one of these components, and you reduce the Hitchin or that's possible. So the group here is not really unitary group, but this is linear, well, real group plus complex group.
I see the other direction to think about.
But,
No,
okay.
Okay, let's thank again for the meal.
Reception, but we would like to.
Let's-
Thank you.